All right, let's talk about DNS. Now, I know what you're thinking. Oh, the phone book of the internet. And yeah, sure, that's true, but it's also selling it way short. We're going to see how it's actually one of the most powerful tools we have for designing massive, resilient systems.
So, to really get why DNS is so important, let's kick things off with a total nightmare scenario. Picture this: you're on call, it's 3 a.m., and the alerts start firing. Everything is down. Your website, your APIs, your databases, the whole thing. Just gone.
Well, that's pretty much exactly what happens when DNS breaks. See, it's not just one service failing. It's like the entire digital ground beneath your feet just crumbles. It's the foundation for everything. And this quote, man, it just says it all, right? Your whole application stack, it just collapses. Before your app can do anything at all, before a single byte of data can be sent, a DNS lookup has to succeed. It's literally the first domino in the chain. If it doesn't tip over, nothing else moves. Game over. Okay, so if we want to learn how to use this thing, we've got to understand how it actually works under the hood. So let's do that. Let's follow the incredible journey of a single DNS query as it travels across the entire internet, just trying to get an answer. This right here, this is our roadmap. Our little story starts with you, the client, and it's going to hit every single one of these stops. We're going to meet each of these servers and figure out exactly what part they play in connecting you to, well, everything you do online. Our first stop is the recursive resolver. You can think of this guy as a private detective. It doesn't have the answer itself, but man, it knows exactly who to go ask to crack the case. This is usually your internet provider, or maybe a public one you've heard of, like Google's 8.8.8.8 or Cloudflare's 1.1.1.1. So the first place our detective goes is to a root DNS server. I like to think of these as the wise old sages sitting at the very, very top of the internet. They don't know the final answer, the specific address, but they give our resolver the first critical clue. They point it in the right general direction, saying, go talk to the top-level domain server. And get this is wild. The entire global internet relies on just 13 of these root server clusters. That's it. Now, of course, they're not just 13 physical machines. They're replicated in hundreds of places all over the world using this really clever networking trick called Anycast. All that means is your question always gets answered by the server that's physically closest to you. Super efficient. Okay, so following that clue from the root server, our resolver now knows to go talk to a TLD server, that's top-level domain. This server is basically the manager for a whole category of domains, like everything ending in .com or .org or .dev. It still doesn't have the final answer, but it gives us the next piece of the puzzle, where to find the actual server that knows. And that finally brings us to our last stop, the authoritative DNS server. This is it. The end of the line, the ultimate source of truth for that one specific domain. This is the server that holds the actual records, including the all-important A record, which has the IP address our computer has been looking for this whole time. Mission accomplished. So that was the full epic journey, right? Across the whole internet and back. But here's the plot twist. In the real world, that long trip almost never actually happens. And why is that? One word: caching. It's the secret sauce that makes the internet feel fast. You see, that whole round trip we just described, that can take over 100 milliseconds. Now, I know that doesn't sound like a lot, but when you're used to pages loading instantly, 100 milliseconds is an eternity. It's a noticeable delay. But with caching, the story changes completely. Instead of your request having to travel across the globe, the answer is often stored right nearby. It could be in your browser's cache, your operating system's cache, or, and this is the most common one, on that recursive resolver we met at the beginning. And the result, it's staggering. We're talking less than 1 millisecond. The answer comes back pretty much instantly. This is why the internet feels so fast. The vast, vast majority of the time, your question is answered by a cache nearby, and that whole long journey just gets skipped entirely. So how is all this caching controlled? Well, that's where something called time to live, or TTL, comes in. Every single DNS record has this value, and it's basically an expiration date. It tells any cache, hey, you can hold on to this answer for this long. And this creates a really interesting trade-off for engineers. You can set a short TTL, which means changes happen fast, perfect for critical failover systems, or you can set a long TTL for things that don't change much, like images on a CDN, which gives you amazing performance. In this right here, this is where things get really cool. Because smart system designers realized they could use all these little mechanics, the lookups, the routing, the TTLs, for more than just finding servers. They can use them to actively control and shape internet traffic on a global scale. This is where DNS stops being a phone book and starts being a superpower. Okay, a classic example is DNS load balancing. The simple way to do it is called round robin, where DNS just gives out a different server IP from a list each time. You get this one, you get that one, you get this one. But the really powerful version is Geo-DNS. This is where the DNS server is smart enough to look at where you are and give you the IP address for the server that's physically closest to you. The goal? Minimum latency, maximum speed. So let's make that real. Let's say you're in Germany and you try to visit a website. Without Geo-DNS, you might get sent to a server way over in the US. But with it, the DNS system goes, a request from Germany, and it hands back the IP address for a server in, say, Frankfurt. The difference in speed is huge. It's a much, much better experience for the user. But wait, what happens if that server in Frankfurt suddenly goes offline? That's where another superpower comes in, DNS failover. See, by combining health checks with those short TTLs we talked about, the DNS system can detect that a server is down. And what does it do? It just automatically starts giving out the IP address of a healthy backup server, maybe one in Ireland or Paris. It's your first line of defense for keeping your service online no matter what. Okay, so let's zoom out and put this all together. When you're building really big global systems, DNS is not just some utility that you set and forget. Not at all. It's a living, breathing, strategic control plane that you can use to influence pretty much every part of your system's architecture. And this table really wraps it all up nicely. You want to talk about scalability? DNS is how you spread traffic across the globe. Performance? That's all about caching and clever geo-routing. Availability? You bet, that's your regional failover right there. It even helps tiny microservices find each other inside a complex system. It's everywhere. So that brings us right back to where we started. After everything we've seen, how it steers global traffic, how it provides instant failover, how it's the key to massive scale, can we really just call DNS a phone book? Or is it something much, much more? Is it actually the ultimate programmable control plane for your entire system?